Okay. Good morning, everybody. This is Eeyore again. I'm not gonna use the hoodie, but it's still me. And today we're gonna check out something quite cool. It's called Evolutionary Solver. Its name is Galapagos, and we're gonna use it in a nice situation, which can happen to you a lot of times, especially now at the end of the semester, where you have some shapes and you want to place them on some piece of sheet material, maybe for laser cutting or something like that, and you really want to save some material, so you want to fit them as tight as possible. This is called nesting. There are many other approaches to this. I've gave you some links to other ways how to optimize your shapes. But I believe Galapagos is very powerful because it's not meant only for this kind of task. It's actually a solver for almost anything you can put into numbers. So this is what it looks like. It's not so long script, but there are some things to understand on the way. So when I just talk in the beginning, I'm just gonna make this run for a while, and you'll see what does it do. So it's like calculating right now. It can be pretty slow, so sometimes if you have some very complex situation, you can keep it running overnight and have the solution in the morning. But the key thing is it's simulating evolution as you know it. So a few words before we jump into that. So in evolution, you have some like entities or some like let's say what's the name for this? Let's say creatures, okay? And those creatures, in this case, our grasshopper solution or the script generates a creature, and this creature should have some kind of features or some kind of let's say some kind of genes, and those genes determine the fitness of that creature. So if you have the gene for blue eyes, maybe you're gonna be attractive for someone or something like that. You know that. And the thing is, if you are able to evaluate this kind of fitness or this kind of like how lovely you are, we're talking about the script all the time, into a number, single number, then you get its fitness, and this fitness value is something we can optimize for. We can either try to minimize it or maximize it, and as you can see, after a few generations over here, oh, you don't see that window, sheesh. Okay, this is very bad. This is why I wanted to switch into Teams. Okay, so I want to show you this on Teams. We're gonna build the script here, but then we jump to Teams because I didn't realize this doesn't work. Funny stuff. Okay, so there's a window, you don't see it. And I'm talking about evolution. It's moving over here. That's good. Okay, so I was talking about the fitness value. That's this value over here. And if you are able to calculate a single number from everything which is happening here in the viewport for every single solution of your script, then you can assign that solution a fitness value, and then survival of the fittest. I mean, the best values mean the genes are good, and we keep those genes. And if we keep those genes, then we're gonna have some cool solutions to your problem. So I hope this kind of makes sense. I'm just gonna try to randomize this a little bit, and you see how troublesome this can get. If I randomize this even more, they are overlapping again. If I randomize this, they are rotating differently. I can randomize this, they are even flipping. So it's about fine-tuning these numbers over here, and doing this by hand would be like, you can do it, You can move this little fella in the X direction and in the Y direction, right? But that's maybe not so much fun. So what I would like to do is build the script, and then you can try to run your evolution by yourself. And we're gonna discuss some stuff on the teams later. So let's jump into a new file. And I'm gonna go to my shaded view because the grid is gonna help this time. I know that the grid has 200 units by default in the millimeters file. So we're gonna use this to help us so that we don't have to restrain everything. So just go to Rhino. Yeah, I'm just gonna hide these guys and use a polyline tool to draw some shapes. Don't make them too big, but make sure that at least one of the shapes has something like a U or C shape, so that we see if it performs nicely. Something should be fitted inside of this hole, in this gap here, right? You can generate another shape by just alt dragging and maybe changing a few points around here. So if I make this slightly shorter, and maybe I'm just gonna take this point over here and place it like maybe inside, like crazy shape, and maybe even this one, yeah, something like this. Make sure that the curves are closed, because we're gonna need closed curves only. I'm gonna create a third shape, maybe a crazy triangle-ish thing, yeah. So this, and maybe another one, something which looks like a comb, maybe. Yeah, shape like this. Yeah, it's a Harry Potter, you know, lightning scar thing. Okay, we have some shapes. I'm afraid maybe they are too big, so I'm just gonna scale them down a little bit. When I hold shift and drag one of these squares, it's gonna be proportional in the XY plane, which is kind of useful to know. And I'm gonna drag them just like over here so that they don't overlap that much. It doesn't matter what kind of curves, you can change them quickly. So I'm gonna select all of them. Take a curve component, right click, set multiple curves, you know the drill, right? And now as I have the curves here in Grasshopper, I just need to use this orient thing, very useful if you still don't know it. Make sure this one becomes your go-to tool, because it's perfect. And what I'm gonna do is I'm gonna orient these shapes from A plane to A plane. So I need a plane in which they are. It seems like they're in the XY plane, but we need to give them some kind of anchoring point. So let's ask for if those curves are planar. So the name of the component is planar. Okay, here we go. So I'm asking for the plane of those shapes. It always puts them, if it's polylines, it puts them in the starting point of the polyline. We don't care about that much this time. Sometimes you have to move this maybe to the center or something like that, but it's not important right now. And once we have those planes over here, I can feed them to A, and then all of those curves are going to be placed in the XY plane with the origin in 0, 0, 0 point. So all of them are now over here overlapping, but they moved. That's what we need. And now we're gonna create some planes for those. Well, maybe just points, but we're gonna rotate the planes as well. So let's do something which we could optimize by hand, but that would take a lot of time, and we don't want to do that. That's the Galapagos job. Okay, so first thing, we're gonna need some points, and those points should be running around over here in this area. I think I'm gonna limit it to -100 to 100 or maybe something like that, so it's gonna be a little square around here. So well, there's many ways how to do this, but I think the quickest is using right away Galapagos like pink gene pool thing. And since we know that we have four curves, we're gonna need four x coordinates and four y coordinates, right? So I don't need 10 sliders here. This is like a slider, but then they are all connected. We're gonna need 8 of it. So if you right click this, there's edit, and you can say that you want only 8 of them, and you can set the minimum to -100. Maximum is already on 100, that's fine. And I'm gonna say 3 decimals, maybe 2 decimals are fine for this case. You can always go a little bit more detailed with more decimals, but 2 is okay. The problem is now we have 8 things, and we need to put 4 of them here and 4 of them here, and I really don't want to do this manually. So what I'm gonna do is I'm gonna partition this list. So this is a list, right? And it contains 8 pieces of data. If we partition that list, I think by default this is 3 and 2, so we have to specify how small partitions do we want. So I'm gonna say 2, right? So I want small branches of data with 2 pieces, 2 numbers in them, and you can see that now we have what we wanted. And now we need to feed this over here and this over here. So I believe the easiest thing is to just use list item index item, and ask for the first index and the second index. And we can use this as x and y. So if I go over here, you can right click and say randomize 100%. You're gonna see that the points are scattered around over here. Okay, so we have points. That's cool. We can place XY planes in them, right? And now we can use this in our B in the orient. I'm gonna move this a little bit. What is the problem is that we have data tree over here, so we created a lot of duplicates, and that's not what we want. So if we think about it, over here, if you stop your mouse over there, there's 4 points only, but each point is in a different branch. But in here, there's 4 curves, each all of them in one list. So what we need to do is come over here and say flatten the data. Now we can see that this one went over here, this huge one went over here, this crazy one went over here, the small one is over here. If we randomize this again, they move differently. So that's something we need. I think I'm gonna hide the planes for now. No, maybe not now, but pretty soon, because they get in the view. So we can now move we can play with the position. Okay, that's cool, but we're still missing something like the sheet. So what I'm gonna do is bounding box, and I'm just gonna put it over here. So now each curve has its bounding box, but what we want to do is right click on the middle here and set it to union box. Then we have all of them enclosed in one little curve. One rectangle. This is kind of okay. If you randomize some more, you're gonna see that sometimes it's a good solution, sometimes very bad. And we could actually move each one of them, like this. So that would be really, I don't want to do this like that. But it's just movement, and we need rotation as well. So I'm just gonna copy this gene pool, and I'm gonna change it. This time I need just one number per every point, so it's gonna be just 4, and it's gonna be, I'm gonna give it 3 decimals, but the minimum is 0 and maximum is just 2. We're gonna use radians this time, so 0 is no rotation, 2 times pi is full rotation, 180 degrees. So I can use this plane and use component called plane rotation, rotate plane, to use these angles over there. So before I use it in the orient, I first take my planes, I rotate each one of them, see, each one is rotating, I can randomize it again, and then I use these over here in B. So now I have 2 things, and frankly, if it comes to this nesting task, usually position and rotation are the most important. Sometimes you even want to flip the orientation, like mirror it or something like that. We can try that later, but let's for the sake of simplicity, let's keep it like this. So these are my genes here, and this is my geometry, and I'm actually missing one last thing, and that's the fitness value. So I believe I can hide the planes because they are somehow intrusive, but you can see that it rotates, right? All of them. Cool. So we need one more last thing, and that's the fitness value. And this can be a little bit tricky because we don't want the curves to overlap, right? This is not a good solution. So we somehow need to say that this box, this union box around it, has to be as small as possible. So that's quite easy. We can take this box, and if you put it into a panel, you're gonna see that it's a flat box, so we can treat it like a rectangle. So we can directly calculate its area. So this is over here. The area is like, it's gonna be a huge number because I'm in millimeters, but that's not a big deal. So yeah, so this is the area. So we want this to be as small as possible, right? So we don't care about the format right now, but we want this to be as small as possible. Okay, so that could be our fitness function, but also we somehow need to get rid of solutions where things overlap. So when I just simulate this again, this is a bad solution, right? This is not a good y-axis gene for this shape, or the other one, we don't know. So there's a way how to solve this pretty quickly, using the grasshopper collision many with many, because we care about collision, all of them together. And we're just asking for how many collisions are there. So if you check out the data, this is just telling you if there is a collision or not. Yeah, we don't use it for the for the bounding box. Of course, we're gonna use it for the curves. So this now says that these two are in a collision and these two are not. Okay, good, but it's not a number, and we cannot use it with this, right? So we need to do something, and actually we don't care about which one is colliding with which one. We care about the number of collisions, right? So if the number of collisions is 0, that's perfect. Okay, so there are many ways how to do this. It's just trusting your gut, your math gut maybe with this. So I'm just gonna do mass addition here to calculate how many things are overlapping. And to simplify this a little bit, I can use this, like this type of data. It's Boolean, right? It's true and false values, but I can cast it to an integer, And then it's gonna say true means 1, 0 means false, right? So now it's numbers, and I can add them together using the mass multiplication. So if I do it like this, you're gonna see that the total of collisions is 2. Okay, that's a number. This is a number, so we're getting close. We can, I don't know, multiply this, but see, this number is very small, and this number is very huge. So we can do something like a penalty, calculation here. So if your area is this, it's kind of okay, but it's not so great. But if you have at least one conflict in there, it's very, very bad. So this has to be very strong. So what I usually do is I take this number and I do some kind of expression on it. And we're gonna play with this a little bit, but we need just one input, so I'm just gonna get rid of that. I'm gonna put it over here, and I'm gonna double click. Oh, you don't see it again, but I'm gonna do x times well, let's do 1000 for the beginning. So we have 1000, and now this is like a huge number, right? It's 2000, and still not so huge like this one, but I want it to have some freedom. We're gonna see that this is not gonna work, but I just want to arrive to some conclusion here. So now we have this number and this number. We can treat this number differently, and the next step is just usually multiplication. So the area gets multiplied by this penalty for collisions. If this collision is if there are 0 collisions, this disappears. That's good, right? So okay, that's fine. And this is something we can actually call our fitness value. So it's a huge number, but fitness value. Okay, so this huge number is something we really want to be as small as possible. So the last step we need, this is, I'm just gonna make some groups, and just to be nicely separated, I'm just gonna place a container over here. Yeah, like this and like that. So this is my fitness value calculation. Yes, and well, this is my geometry, right? And sorry, and these are my genes, so well, I don't have to put them, they're pink. Genes are always pink. Okay, so the last step is to take the Galapagos component, and it has these weird inputs and outputs. They are actually not kind of inputs, but this is an input, but you drag the cable from that towards a number, and then it starts working with that. So this is our fitness value. We can see it over here, and it goes into the fitness. And the genome, well, those are all the genes. You can assign this to sliders, but also, of course, to these gene boxes. And it works the same. You have to hold down Shift if you want to have more boxes than one. So with Shift, I'm adding this second option there, and that's our Galapagos setup. So I believe we can just move this down a little bit, and let's take it for a spin. So, oh, there's a question. Oh yeah, to change the expression, you just double click it, the middle, and then you can just delete everything which is there and just type x asterisk 1000 or something like that. Cool question, by the way. Thanks. Okay, so I'm gonna take it for a spin now. Just double clicking here, double clicking. Awesome. And you always get to this first page. There's like this is a very cool read. So maybe if you're bored in Corona separation, well, it stopped today, but whatever. Um, you can read this stuff. That's actually very interesting stuff about like how it's working internally and so on. But in this page, we're actually most interested in this first thing here, and that's like what should we do with the fitness. By default it's set to maximize. If you click the minus, it's going to be minimizing, and that's our case, right? We want the area to be as small as possible, and we don't want any collisions, right? So minimize is what we do. These are some parameters. We're gonna talk about them maybe later. Maybe, oh shit, you don't see this. Sorry. Okay, yeah, I just realized. So this is for the discussion on Teams, but I'm just gonna start running this so that you see something moving. Oh yeah. So as you see, it's moving like this, and that means like right now the first generation is totally random, so it just fills the data in. So every single curve has, you know, 2 numbers for position, 1 number for rotation, and we need to create at least, I think it was 50 entities or 50 creatures. And after you have 50 creatures, you sort them along their, you know, fitness value, and you keep just 10% of the best ones. Discard all the rest, and then you go to the second phase where you just pick random pairs and somehow like pair up their genes. So if your mother had you know, X position of 300, you're gonna keep it for the child, but you take the father's Y position or something like that. You cross those genes, and then you create a new population, and you know, that's how you do it. So this is what happens. But we still have one problem, and you can see that it doesn't shrink that much. And the problem is, you don't see it in my window, but the problem is we are getting a lot of zeros in here. So I'm gonna just stop it right now. Click OK, and you see that our fitness value is 0. And if I change the position here, well, you know, I changed something, but the fitness value is still 0. And the problem is this you know, this situation where we realize that, you know, if this is 0, then it cancels out at this one, and that's not a good thing. So there are 2 things what we can do, and one is just get rid of the multiplication and make addition, because when you add 0, it's actually, you know, good. But then I would increase this number over here. That's one solution. Or we can try to say x minus 1, or I mean minus 2. Oh yeah, okay. Now, oh yeah, let's do the addition. That's maybe better because you don't see my screen. So instead of this, I'm just gonna disable that, and I'm gonna add addition. So if there are no collisions, I add 0, and it's all about the area. So that kind of makes sense to me. So now if I change something over here, so I'm going to change this. Oh, there's a collision. So I'm going to change this. Yeah, you're going to see that this number increased, right? So we're going to use this as our new fitness value. And if we look at the, you know, this is still like in tens of thousands, so I would increase this to 10,000 as well. So this is one solution to this problem. Maybe I just delete this. There are other ways. You can just do x minus something times something huge, and if this is 0, then it kind of keeps to be 1 or something like that. But I believe this is better, so I'm gonna run it once more. Minimize. You don't see it, I know. So I'm just gonna keep it running, and it should start shrinking. As I said, we have just four things, so it's quite quick. If you had like 300 things, that's gonna be a lot of genes, and you can get pretty slow. But that's not a bad thing. You can keep it running overnight or something like that. That's what people do with complex simulations. So if you're ready with your curves, you just keep it running for an hour or something like that, and gradually you should arrive to some nice layout of things so that they don't overlap, and you can have less leftovers in your sheet material. Okay, I'm sorry for not realizing that the Galapagos window is not visible on YouTube stream, because I still didn't work it out. So I think it's time to jump to Teams to maybe discuss the window. So I would end this if there are no direct questions right now, and let's jump into Teams and discuss stuff over there. Mm-hmm. Okay, let's go to Teams then.